Hi everyone, I hope you're doing well. At this point, I'm sure you're probably aware that we only have 2 weeks left in the semester, uh, which feels crazy, but also, you know, exciting, right? That you could finally be done with this and move on. Anyways, what I put together today is kind of like a review video for the final exam. So it's just an optional thing if you want any help while you're preparing for the final exam. I've picked out some questions that I think covers uh, a wide variety of topics that we've seen in this class, so it might be a good review. And maybe it might help with some of these later sections if you're having any questions from them. I did include questions from all the later material as well. So anyways, hopefully this video is helpful to you. If you have any questions about anything from the video or any questions covered, feel free to email me. I'll also post a document of the completed review that I did in the video, so if you prefer to learn that way as well, that will be available to you. So anyways, hopefully it helps. For the final exam, you will have access to the derivative rules and the integral rules. But if you are moving on to the next calculus class, the more that you can memorize those rules, the better, because you will most likely need to have them memorized for that next class. In this class, we're just kind of focusing on using the rules. Okay, so let's work on some of these derivatives. For problem 1, this is a derivative where we're going to be able to use the power rule. And anytime you're taking a derivative, I think it's always good to consider what rule or rules you will need first before you start actually solving the problem. And so remember, the power rule is like if it is, a variable to an exponent. So all of these that we have here can be written like that. Even the x can be rewritten as x to the 1, and that's why we can apply the power rule. And then the other one, whenever we have an x in the denominator, you can bring it out of the denominator, pull it to the numerator, but at the same time you make the exponent negative. So this is just rewriting the function. I haven't taken any derivatives yet. Now let's take the derivative using the power rule. And so the derivative rule here is that you bring the exponent down and then you subtract 1 from the exponent. So the derivative here is going to be 9, because if you ever have just a coefficient in the front, it just stays in front. And then the derivative of x squared is 2x to the 1. And minus 5 times 1x, and then we subtract 1 from the exponent, so that becomes a 0, minus 3 times negative 2x, and then you want to be careful when you're dealing with a negative, because if I have negative 2 subtracting 1, that actually, the number itself gets larger, and it becomes negative 3. And then at this point I'll simplify. So we've got 18x minus, so anything raised to the 0 is just 1, so that's just going to be minus 5 plus 6x to the negative 3. And I'm just going to take it one step further here, because typically, as a general rule for these math problems, is that you want to write the answer in a similar form to how the question was given. So in this case, for that reason, I'm just going to go ahead and rewrite x to the negative 1/3 as x to the positive 3 in the denominator. And I think I misspoke there. So 6x to the negative 3 becomes 6 over x to the 3. And that's the final answer. Again, the only derivative rule we really used was the power rule. Here's another derivative, and this time what we're going to need is the quotient rule. For the most part, people are usually able to identify the quotient rule because of the fraction. So in this case, now let's take the derivative. Obviously you have the formula in front of you. For me, without the formula, I just know that when I'm taking the quotient rule, the first thing I do is rewrite the denominator, and that usually helps to figure out the rest from here. So if the denominator is rewritten, then the next thing I multiply by is the derivative of the numerator. So in this case, the derivative of the numerator is 3. Minus, now I'm going to kind of flip that. So the numerator will get left alone. But now I take the derivative of the denominator, which is 6, all over the denominator squared. And now let's simplify. So what I'll do in each case is I'll go ahead, like for this first multiplication here, I'll distribute the 3. So we've got 18x plus 3, and if I distribute the 6 in that other multiplication there, we've got 18x minus 48. And I'd probably say the main issues I see with the quotient rule is really more of arithmetic stuff, which specifically has to do with the negative here. So a lot of times people would distribute the 6 here and then just kind of drop the parentheses, so only that first term would be negative. But we want to be really careful with the negatives. That's one of those places that where people will have the right idea and they make the error, and it's, I don't know, 85% of the time it's because of a negative. So in this case, what I did to try and help that is I kept that second part all in parentheses to kind of remind myself, okay, I haven't done anything with this negative yet, so now I need to make sure it gets distributed to both terms. And so that becomes 18x plus 3 minus 18x plus 48. And in this case, the 18s will cancel. And the final answer is 51 over 6x plus 1 squared. Okay, here's another derivative problem. So here, I'm going to rewrite it, because when taking derivatives in general, we don't want to leave the radical or the square root, because we want to rewrite it with the exponent, because then that means we can apply the power rule. So again, thinking before I take the derivative, what rules am I going to use? I'm going to use the power rule, but I'm actually also going to use the chain rule. So why I'm going to use the chain rule is just the fact that this part, normally the power rule is just like some variable raised to an exponent, when that base is something more than just an x. That's what tells us to use the chain rule. And basically we're going to take the derivative using the same exact way that we would use the power rule, but the extra part is that at the end we multiply by the derivative of that inside. So that's the extra part here. And I might actually, let me switch colors here real quick, because I think the best way to illustrate this is to just rewrite the problem where the base is now just an x. Right, so this would be an example of how we would take the derivative if we don't need the chain rule, because there's nothing more complicated in the base. The base is just a single variable, in this case an x. So then if we take the derivative, the 4 is the constant in the front, so I'm just going to leave it as a 4. We already talked about how the power rule, you bring the exponent down, which in this case is 1/2 x, and I'll just write it out this time. Becomes to the 1/2, and then we minus 1. And with fractions, we need to get common denominators here to solve this. So let me just, I'm not going to simplify that first part yet, but I just want to show that the exponent ends up being a negative 1/2. So simplifying further, the 4 times 1/2, so it should just be 2x to the negative 1/2. And if we wanted to write it the same way that the problem was given to us, we could rewrite it as 2 square root of x. Okay, so how does that apply to our current problem? Let's go ahead and try to do the same thing. So first, I'll leave the 4 alone. I also, at this point, oops, I don't want to write that yet, because now I'm going to start applying the power rule. So I'm going to bring the exponent down, which is the 1/2. The 8 x squared plus 3 is that original base. At this part of the problem, we don't change it. It stays as 8x squared plus 3. And then now we write the new exponent. I'm not going to write it all out again because we already did it down here. But the new exponent would basically be 1/2 minus 1, which ends up being negative 1/2. And now the last part is the chain rule part. So now this extra step, which we did not do when we looked at that g of x below, is that now we multiply by the derivative of that base, which is now more complicated, the part inside the parentheses. So the derivative would be 8 times 2x. So this is the answer. Now we would just like simplify. So I've got f prime of x is equal to, I'll go ahead and do the 4 times 1/2, so that's 2 times 8x squared plus 3 to the negative 1/2 times 16x. And so what I will go ahead and do is it's multiplied at the end. I'll go ahead and multiply it with the 2 because that'll simplify it a little bit more. So we'll get 32x times 8x squared plus 3 to the negative 1/2. And I just realized you might have caught this mistake already, that I was kind of lazy the part that I was working at in green. So kudos to you if you caught that. Sorry if I've confused you. So I wrote it as square root of x. That would have been if it was just x to the positive 1/2, but the negative 1/2 means it needs to go in the denominator. So this one should have been 2 over square root of x. Okay, so now let me go back to this problem. This is the, this is the correct answer. This is mostly simplified. But if I do want to write it the same format as the original problem was given, I could just, the negative 1/2 exponent, I can move the whole thing to the denominator to make it positive. And the half exponent can change it to the square root. So let me rewrite this as 32x over the square root of 8x squared plus 3. And that is the final answer for this one. Okay, number 4, here's another derivative. So looking at this one, I see that I've got an e in there. So we have a specific derivative rule for e, which, is somewhat straightforward, and that derivative of e to the x is just e to the x. But we are going to have to apply the chain rule here, because again, when something is more complicated, now the exponent is not just an x, it's a 4x. So the derivative for that would actually be e to the 4x. And now this is actually using the chain rule again. So to take the derivative of e to the 4x, we would need to use the chain rule. So the rules so far I've talked about is just there's an e to the x rule, there's a chain rule, and there's actually also one other main rule that we would need to solve this problem, and it's the product rule. So why do we have to use the product rule? Well, if you have a problem where, like, in this case, you could almost look at it as kind of like the coefficient, but it's not, because like all the other ones we've looked at, there haven't been any variables in there. So like if I look back at some of these other problems, so like right here, that's just a 4. So it's just a constant in the front, so that's a coefficient, which means we can just leave it in the front and then take the derivative of the other part. Going up to number 1 as well, same thing here, there was a lot of coefficients. So that's just a 9 in the front. This is just a 5 in the front. And so the derivative rule is basically just like if there's a coefficient in the front, you can just leave that alone and then multiply it by the derivative you find. But in this case, what's happening is I have 2 different functions multiplied together. So let me zoom in here a little bit. So I've got this, and then I've got that function. So you could say it's like function 1 and function 2. And because they're multiplied together, that means that I need to use the product rule. Okay, so let's go ahead and use the product rule here. Because the product rule is addition in between, it doesn't really matter which one you use first as the original function and which one you use first as the derivative. And I'm going to solve this problem all together, but I know that a lot of people will break it up into steps. But for me, I try to keep it kind of consistent with the quotient rule so I don't get them mixed up. So I actually start by rewriting the e to the 4x first, because for me it's kind of like with the quotient rule that I start by just writing the denominator first. So it's sort of like in either case I just write the second thing first, leaving it alone, not taking any derivatives. So that's function 2. Then I need to multiply by the derivative of function 1, which is 3x, and the derivative of that is 3. And then now it's the product rule, so I do addition instead of subtraction, and then I just switch these around. So now I'm going to write the 3x, not taking any derivatives, and then I'm going to multiply by the derivative of e to the 4x, which we already talked about. That derivative is 4e to the 4x. There's not much I can simplify here, but I can do a little bit of combining. So I'd say the final answer here, we could write it as 3e to the 4x plus 12x e to the 4x. And there is some stuff that we could simplify here. You can honestly, since they both have a 3 and an e to the 4x in there, you could factor that out, but you don't need to do that. I'll go ahead and write that just in case you're curious. So if you factor out the e to the 4x, that would become 1 plus 4x. And these are the same thing. But for our purposes in this class, you can go ahead and leave it like this. And one other comment about this is, let's say in this problem, if that x in function 1 was not there, so I'm going to label this as a different function, g of x instead. If we have 3e to the 4x, let's say, if you want to take the derivative of this function, this would be a situation where you do not need to use the product rule. And that's because now in front it's just a 3, so you don't have to treat it like a different function. You could just say that 3 is in front of that function e to the 4x. So to take the derivative, I would just leave the 3 there and then take the derivative of e to the 4x, which we've already said is 4e to the 4x. And then let me go ahead and multiply here. 12 e to the 4x. So that would be the answer in that case. Okay, now let's look at an application type problem using derivatives. So one reason we would use derivatives is that we can get more information about our graphs. So like, is something increasing or decreasing? And it's not just about the graph. I mean, we look at functions like this. We don't really know what the variables stand for, but like we have, for example, dealt with a lot of business applications. So we might want to know, when is profit increasing? When is profit decreasing? So that's when we would use the first derivative to find increasing and decreasing. And then we also might look at, okay, so let's say profit is increasing. Is that increase increasing? Like, is it jumping up more and more each time? Or is that increase decreasing? So that's kind of what concavity is telling us, is like, is that increase, is it slowing down? Is it speeding up? You could look at the same thing if you were looking at a decrease as well. So that's a little background behind it, but so for this problem, we're looking at concavity. So we want to know, okay, that means second derivative. So we have to take the derivative and then take the derivative of again. Let's take the first derivative. And before we take the second derivative, we'll go ahead and simplify this first. Now we can take the second derivative, which is just taking the derivative again. Okay, once you get to this point, we want to set it equal to 0 and find where it's equal to 0. If we were working with the first derivative, that would tell us critical numbers. Since we're dealing with the second derivative, setting it equal to 0 tells us about inflection points, or points where it can change in concavity. And in this case, we get that x equals x equals to 2 is the place where we expect there to be an inflection point. So how do we check it? What we do is we draw a number line here, and we're trying to figure out on the left or right, does it actually change in concavity? So that would be, does it change from positive to negative or negative to positive? So that would confirm it's an inflection point if it does that. So what we do is we choose a point on either side, and I always put that value in parentheses to remind myself that it's not an actual point, like it's not a point of inflection or critical number, it's just a point that I'm choosing in the interval to plug in. So then you plug it into that first derivative and see what you get. So here, let me say if I plug it into that first derivative, I have negative 12 times 0 plus 24, which is 24. That's positive. So it's concave up on that interval from negative infinity to 2. And now let's check the point 3. Negative 12 times 3 plus 24. And here we see we're going to get a negative answer. So it's concave down on that interval. So now let me write all of our final answers here. So there's an inflection point at x equals 2. And it's concave up on that first interval, so that would be negative infinity to 2, and it's concave down from 2 to infinity. And those are our final answers for this one. Okay, let's look at another application. Here we have cost function and a price function. And then we want to figure out maximum profit. So the first thing we need to do is find the profit function before we take any kind of derivatives. So this is another formula sheet that you have access to. But profit is revenue minus cost. We don't have revenue yet, but you can actually interpret revenue as the number of units times the price, right? That's how much money, if you break it down to its bare essentials. If you had a company that was selling something, if you took the price and multiplied by how many units you sold, that would be the revenue. So here that means I can take x and multiply it by our profit function, which is 65 minus x. So revenue is 65x minus x squared. So now we can go ahead and finally get to our profit function. So that's revenue minus cost. So we've got 65x, I'm writing the revenue first, minus x squared, minus, now we subtract our cost function, which we're given, 90 plus 17x. Just going to rewrite it all out right now, distributing that negative. So we get minus 90 minus 17x. So finally, we get to our profit function, which is going to be, I like to rewrite it with like the largest exponent first and go down from there. So we got negative x squared, and then we can combine the 65x minus the 17x to get positive 48x minus 90. We're trying to find the maximum profit, so that means maximum and minimums is like increasing and decreasing. So we find them by taking the derivative and setting them equal to 0. And that's At least that would give us the critical numbers, which is what we need in this problem. So let's take the derivative. And set it equal to 0. So here this tells us our critical number. If we wanted to check, in this case we're only given one critical number, so we can assume it's going to be the maximum, but to double check you could always draw a number line, just like what we had done in the previous problem. Let's say if we put 1 here, 25 here, and you'd plug it into that derivative function to see if it's positive and negative. In this case we'd want it to go from positive to negative. So let's see, if we plug it in, if we plug in 1, we get 46, which is positive. So that means the function goes up. If we plug in 25, we get -2, which is negative, which means then after that it goes down. So it kind of confirms that that point that we're looking at is where it hits its peak or its maximum. So we want to actually find the maximum profit. So this would be a point where we would take this x value that we found, and now we're going to go back to the original profit function and plug it in to find what the profit is from selling 24 units. You should end up, once you plug that in, is $486. There's nothing in this problem indicating that profit is in thousands or anything like that, which means we can just leave the answer as it is. Now let's look at implicit differentiation. With implicit differentiation, we can just pretty much take the derivatives using all of the derivative rules we have been using in the class. The extra thing is that whenever we're taking the derivative of something that has a y in it, we always need to have that extra step of multiplying by a dy dx. But other than that, the derivative stuff is the same. So let's say if we want to take the derivative here, this first part, 3x cubed, okay, well that's just x's, so I'm just going to take the derivative as I would normally take it without doing anything extra. So I've got 3 times 3x squared. Okay, now plus, now we're going to take the derivative of 3y. So the first step is really to just take the derivative as you would if it were like a 3x. So the way that you would take the derivative of that would just say 3. Right, and that's because as a side note, if we had 3x, we would say the derivative is 3. So now if we have 3y, we would say that the derivative is also 3. However, since it's implicit here, we took the derivative of a different variable. This is where we have to multiply in the dy dx. So that's the new part, the different part. Okay, equals. Now we want to take the derivative of 2y squared. So first, just take the derivative and don't worry about the y. So that's going to be 2 times 2y. So if it were an x, we would be done at this point, but again, because it's a y, the last step is to multiply by dy dx. So let me simplify what I have here. So that's 9x squared plus 3 dy dx is equal to 4y dy dx. So we're trying to find dy dx, which is actually what we had been doing in all of our other problems. It was just like y was by itself on the other side of the equation. Now what makes us implicit is that the y's are kind of all mixed in our equation. And so this is definitely an extra step that we didn't do in our other problems. But now we just have to isolate dy dx's to get dy dx is equal to, and then that's going to be our final answer. Okay, so we can do that. But first I want to group everything with a dy dx on one side of the equation. It actually doesn't matter which side I move them over to. Maybe I'll go ahead and move the part on the left over to the right. I'm going to subtract that from both sides, which leaves 9x squared is equal to 4y dy dx minus 3 dy dx. So the technique here is if you get everything with the dy dx on one side, then you could factor it out, and that gives you a single dy dx instead of more than one, which we have in the problem right now. So if I factor it out, that leaves 4y minus 3 in parentheses here. So finally, to get dy dx by itself, I would divide both sides by the 4y minus 3. And that gives us our final answer. dy dx is equal to 9x squared over 4y minus 3. Okay, these last few problems deal with integrals. So integrals and derivatives are very much related. They're basically inverse operations. So when we're evaluating integrals like these, we're doing the opposite of what we had been doing before. And it's sort of hard to wrap our mind around because we're so used to it at this point. In the class, we've just done derivatives so much. So let's start with this one. So this is an example where we're using the integral power rule. And so one thing that's different is instead of subtracting 1 from the exponent, we're adding 1 to the exponent. The other thing that's different is instead of multiplying in the front, we're dividing by it. So the integral rule, oops, that's not what I wanted. The integral rule for something raised to the power of n is, now the exponent is n plus 1. And instead of multiplying that in the front, we're dividing by it as well. One thing that I would strongly recommend in this class whenever you're doing an integral is to check your work by taking the derivative at the end to see if you get back to that original problem. Because for most people, at this point, they're much more comfortable with derivatives. So you can always use that to check your work. Okay, so let's go ahead and take the integral here. One thing I will say is you might want to rewrite some of the things. So like this you could rewrite as x to the negative 3. So just like with taking the derivative, it puts it in a form that it's like you can see how it's related to the power rule. And you could do the same thing here. You may not necessarily. I'll talk about that in a second. Okay, so let's start integrating. So one thing that's the same with derivatives is like in this first one, there's a 10 in the front, and you can just leave the 10 there, and then you take the integral of x to the third. So now instead of subtracting, we're adding. So the exponent is going to be a 4, and then you put it over a 4. So that's the integral power rule. Plus, now we want to integrate 1 over x. Let's say if you were like just going to use the power rule for this one, you'd be like, oh, okay, I've got an x, I have to add 1 to it, and what that gives me is a 0 over 0, and then you might be like, wait a minute, this is weird, I can't divide by 0, this doesn't make any sense. There's a reason this doesn't make any sense, and that's because the rule we need here is ln. So if you look at the integral rules, the integral for 1 over x is ln of x, and that's because, I'll erase this in a second, if you had the function ln of x, if you took the derivative, The derivative rule is that that becomes 1 over x. So now we're just going in the reverse direction. It's kind of like starting off in the derivative and coming back to the original. So the integral of 1 over x is ln of x. So I just kind of like to show what would happen if you forgot about it, because we use the power rule so much more that we just get in the habit of just doing it automatically. But if you tried to do the power rule there, you would run into a problem. It just wouldn't look right. So now I'm going to write this as ln of x, and then plus, we rewrote it as x to the negative 3, so now if I integrate that using the power rule, it becomes x. So we're going to add 1 to the exponent, so it's going to be negative 2 over negative 2, and then minus 5x. And so there's two types of integrals. There's the indefinite integral and the definite integral. So indefinite is if there's no numbers on this integral sign, and then that means the last step is to just add c to the end. Okay, so let me go ahead here and rewrite our problem. There's not much simplifying to do. I guess for 10 divided by 4, I could change that to 5 over 2 x to the 4 plus ln of x minus 1/2 x to the negative 2 minus 5x plus c. So this is actually the final answer. But I had mentioned checking your work. So if you want to check your work, the way you can do that is take the derivative. So to do that, okay, 5 over 2 times the derivative of x to the 4th, which is 4x cubed, plus derivative of ln of x is 1 over x minus 1/2 times the derivative of x to the negative 2, which is negative 2x to the negative 3 minus 5. And then the reason we have the plus c there is it's basically like no matter what number it is, if you take the derivative, it just goes to 0. And so simplifying this, we get 10x to the 3rd plus 1 over x plus x to the negative 3rd, which is the same thing as 1 over x cubed, minus 5, which was exactly what we had in that original integral in the parentheses there. Okay, let's look at this integral. Kind of what I was talking about before with indefinite versus definite. It doesn't have any numbers on the integral sign, so this is an indefinite integral again, which means in our answer we're going to have the plus c there. The other thing that's happening here is there's just like a little bit more going on. It's like you're not quite sure how to take the derivative here. If your mind is still like very much thinking about derivatives, you might have this instinct to like, I want to take the product rule. The problem is that there is no product rule for integrals. There's no product rule for integrals, and there's no quotient rule for integrals. So that is when we use substitution. And when you use substitution should be that you could look at the problem and part of the, how do I put it, like part of the derivative and the original problem are kind of both in there. And so what I mean by that is like in this particular one, yeah, we have an e to the x squared. If I took that derivative, it would be e to the x squared times 2x. So that part of the derivative 2x is like kind of there. So that's like an indication of maybe to use the substitution. But I'd say another way of like when do you try substitution is that if it looks like a product rule or a quotient rule for derivatives, chances are you need to use the substitution rule. The way that we select what to try and set u equal to is we try to find something in there where its derivative is also in the integral. And so for this one, I'm going to actually let u be x squared. Then if I take the derivative of that, which is du over dx, I would get 2x. So that's because the 10x in the front is like very similar to that derivative we just found. And then I'm going to rewrite this as du is equal to 2x dx. And now I'm going to start substituting things back in. First, let me rewrite my problem a little bit. 10x e to the x squared. So I see the u, that could go right for that exponent of e, but then I have this 2x where here I have a 10x. So sometimes you might need to do a little bit, like in this case, one thing I might say is, well, 10, I could just rewrite that as 5 times 2. So I'm going to rewrite this integral as 5, because if it's just a constant, you can bring it to the front. It's not really part of the integral. But the 2x I'm going to leave in there. E to the x squared dx. And now we can start our substitutions. So the x squared, I'm going to replace that with a u. But then I also have this 2x dx here that I am going to replace with du. So rewriting the problem, that's 5 times the integral of e to the u du. And now this is something we can take the integral of, because we don't need anything like a product rule anymore. The integral of e to the u is just e to the u, so I'm going to write that as 5 e to the u, and it's indefinite, so I'm going to put plus c. Of course, when you are using substitution, you always have to substitute back at the end, because u was not part of our original problem. So I'm going to rewrite this as 5e to the x squared plus c, and that is our final answer. In the last problem I mentioned to check your work by taking the derivative, and that's definitely true for substitution problems. Substitution problems are harder for sure. So it's always good to go back and just take the derivative and see if you get back to what that original expression was. So here, let's go ahead and check by taking the derivative. So that would be 5 times e to the x squared times 2x. And then the derivative of c is 0, but we use the chain rule here to take the derivative of e to the x squared. So if we simplify this, this becomes 10x e to the x squared, which is exactly what we had in our integral. Okay, here's the last question I have on this review document for this video. Excuse me. All right, so this is the one where there's numbers here, so that is a definite integral. It tells me that I don't need a plus c at the end. Instead, I'm going to do subtraction using the fundamental theorem of calculus. But before we do that, let's first just take the integral, because those rules are going to be the same, those first steps. So the integral for 2x would be 2. I just feel like rewriting it for some reason. Okay, so now when we take the integral, 2 times, this is going to end up being x squared over 2 plus 9x. So this is where, again, if it were indefinite, you would add the c, but I'm not going to do that in this case. So simplifying this, I get x squared plus 9x. And before we go any further, maybe I might check my work again by taking the derivative. So the derivative is 2x plus 9. So it checks out. So that's the correct integral. Now we're going to use that fundamental theorem of calculus. Notation-wise, once I take the integral, I put it in these brackets and then I put the numbers on the outside. So that tells me, okay, I've already taken the integral, so that part's done, but now I still need to plug in my numbers. So you plug in 4, and then you subtract, and you plug in 3. So it'll look like 4 squared plus 9 times 4 minus 3 squared plus 9 times 3. And then I just have to evaluate this to get my final answer. And the final answer is 16. And it doesn't ask about that, but there was some stuff that we've covered already, which is like what we're actually trying to find is an area here. So we found the area under that curve between the points x3 to x4 would be at 16 square units. Now, but for this problem, we don't need to talk about anything like that. We just write our answer down as 16. So hopefully that helps. If you have any questions about any of these problems or anything while you're reviewing for the final exam, please feel free to send me an email.